Okay, it's my pleasure to introduce Yuta Kikuchi. He received his undergraduate degree at the University of Tokyo and his doctorate from Kyoto University with Teiji Kunihiro. He was then a postdoctoral associate at the Riken BNL Research Center, where he's worked with Taku Izubichi at Dima Karjaev and others. And he's interested in non-perturbative aspects of quantum field theory and their applications to high energy nuclear and condensed matter physics. He's presently a Goldhaber Fellow at the Nuclear Theory Group at Brookhaven. You can ask questions during the talk, but we would ask that you do so in the chat to allow for continuity of discussion. With that, Yuta, could you begin, please?
Yeah, thank you for a very nice introduction. It's a pleasure for me to be here. And yeah, today I will talk about a very basic aspect of the quantum computation in order to, in the future, simulate the quantum field theories efficiently. So I will start with my career path, and then after that, I will give some overview of digital quantum simulation and its application to some very simple quantum field theory, so-called Schwinger model. And then I will give some perspective at the end of the talk. So let me start with my career path. So when I was in undergrad, I was interested in both particle physics and condensed matter physics, especially since I learned that quantum field theories serve as important universal tools, which can describe both high energy and low energy physics. And after that, I entered graduate school and I went into a nuclear theory group. At that time, that is just because I thought that it was between particle and condensed matter theory. So, I mean, if you look at the QCD, then that can describe the dynamics of elementary particle. On the other hand, this QCD shows very rich phase diagram, which is very similar to certain condensed matter systems. And during the period, I worked on fluid dynamics, certain anomalous transport induced by anomalies, and also some non-perturbative aspects of QFT. And at this time, I visited Brookhaven National Laboratory for the first time, and also I stayed at Stony Brook University for 2 years. That was the reason why probably I'm here now. And then after that, as a postdoc, I went to Riken BNL Research Center located at Brookhaven National Lab, and I worked on quantum field theories, again, for both high energy and condensed matter theories. But at this point, I started seriously working on quantum information and computing, and it's almost, I think, 3 or 4 years ago. And then now, as a Goldhaber Fellow at Brookhaven National Lab and also research associate at C2QA, I'm working on how to apply the quantum computing for certain classes of quantum field theories. And also another interesting question is how you can use the knowledge of quantum field theories to do efficient quantum computing. So this is my role at C2QA. So basically, I'm working on interdisciplinary research connecting these following topics, that is quantum computing information and high energy nuclear physics, and then also some of the condensed matter physics. Here, I just highlight what is the interesting connection between quantum computing information and high energy nuclear physics. And then I will not go through all of this, but that's just a few of them. So for example, obviously, as I will talk today, people have been working on quantum simulation of quantum field theories for the forthcoming large-scale quantum computer. And that is obviously a hot topic now. And also from theoretical viewpoint, for example, black hole physics is very interesting also for the information theory people. That is related to so-called information paradox, and then there's a very interesting information theoretic understanding. And then also, for example, if you are familiar with topological quantum field theory, then this can be a very good example or very good building blocks to construct some efficient error correction code that will be important for future quantum computing. So these fields, even though these fields seems distinct, but these are tightly connected, and knowing these fields and then see from a bit different perspective would be very helpful. So that is my objective in the C2QA. So that is my brief introduction of career path. So let me jump into more physics, physics. So I will start with covering the digital quantum simulation from this slide. So digital quantum simulation is composed of some quantum operation acting on qubit space, consisting of so-called a qubit state or bunch of qubit state. So a qubit state is given by state 0 and state 1, and also its superposition of this 0 and 1. So it's quite distinct from the classical bit state that is given only by 0 and 1. So the difference is obviously you can expand the expressibility by using superposition between these two states. And then given a bunch of qubits, in order to perform some non-trivial quantum operation, you want to apply unitary gate set and also measurement at the end. And for example, here I prepare so-called universal gate set, a universal gate set. And they are Hadamard gate, CNOT gate, and Z-rotation gate. So I will explain one by one here. So X, Y, Z here, I mean by Pauli X and Y and Z operator. And then on the right-hand side, I have a circuit diagram for this operation. So time flows from left to right. And each wire corresponds to 1 qubit. So, and then this box, for example, represents the gate that you want to apply. So first one is so-called Hadamard gate. So in terms of qubit, this Hadamard gate sends this 0 to the superposition 0 plus 1 over square root of 2. And if input is 1, then this is going to be 0 minus 1. It's also convenient to keep in mind that how Pauli operators are converted under this operation. For example, if you apply this Hadamard gate on Z gate, then you will get X gate. Likewise, you can also look at CNOT gate. So CNOT gate is a 2 qubit gate. So this is the corresponding figure. You have 2 qubit input state. And depending on your upper qubit, you will apply different operation on the lower qubit. And then upper qubit is called control qubit, and then lower qubit is called the target qubit or register. So if your control qubit is 0, you do nothing on the target qubit, but if you have 1, then you will apply X gate. And again, if you look at how this CNOT gate acts on Pauli operators, so this is one example. If you have Z tensor I and then apply CNOT, then you will get Z tensor Z. We will see how this is useful in a moment. And then finally, the last piece is so-called Z-rotation gate. So this is 1 qubit rotation gate, and then Z is the Pauli Z operator. So in order to see how you make use of these operations, or how you do some interesting quantum simulation, example of quantum simulation, let's see how to implement the so-called Hamiltonian evolution or Hamiltonian simulation. And that is given some Hamiltonian H, and then given some initial state, probably you want to apply unitary operator in order to see the real-time evolution of the system. So I have 3 examples here. So let's see one by one. So let's say your Hamiltonian is given by h times x, and then h is just a real parameter, and then x is a power x operator. So this is just a 1 qubit or kind of trivial Hamiltonian. And then you want to apply exponential minus I, th, and x. So this is the Hamiltonian evolution operator in this case. But at least in this universal gate set, you don't have zero rotation gates. So what you can, for example, do is instead of using this exponential ITHX, you can use this HCH is x. So you take a conjugate of this zero rotation gate by h, then this will recover the x rotation gate. So indeed, you can write this unitary evolution by h, zero rotation, and h, like this circuit diagram. So this way you can decompose a unitary operator by using this elementary gate. And another example here is Hamiltonian given by minus j z tensor z. Again, j is some coupling constant, and z tensor z is, well, this is Eisen model. So maybe it's a bit trickier, but let's see. So you want to, again, apply exponential ITJ and z tensor z, but you don't know how to apply exponential z tensor z. But if you remember that C naught operation sends this z tensor I to z tensor z, then you again take a conjugation of this z rotation by C naught. Then you notice that this z rotation is applied only on the first qubit. You do nothing on second qubit. So in the end, you can write down this unitary gate by the sequence of C naught and then our z rotation acting on first qubit and then C naught. So this is a circuit diagram. And having these two ingredients, actually, you can do slightly more interesting simulation. So if you have z tensor z term and x term, then this is a part of so-called transverse field Eisen model. So if you want to see the real-time simulation, real-time evolution, then what you want to do is you want to apply the exponential minus ITH with this Hamiltonian. Now you have this x unitary operation and zz unitary evolution. So it's tempting to do the following. So you have UT, you decompose this UT into x part and zz part. So product form of this first two evolution operators. But as you know, because zz and x don't commute to each other, you cannot just do, you have to use Baker-Campbell-Hausdorff formula, and then you will have a commutator between zz operator, x operator on top of this product form. So in other words, if you try to approximate this UT by this product form, there's going to be some error term. Okay, and then this error term depends on the time duration of t for this evolution operator. So if you want to suppress this factor, this error, what you want to do is you want to take this t to be small. In order to do that, instead of directly implement this UT, you first decompose this UT into the product form. So this U into the M pieces. So the time duration, each time duration is given by T over M. And then if T over M is very small, then this error term is virtually very small. So you can control this error term. And indeed, this evolution operator after writing this into the product form, you will get the error given by a scaling like T squared over M. So if you make this M to be large, if you make this U into very small pieces, and your error is going to be small and small. So this is so-called Suzuki-Trota decomposition, and then very popular technique when it comes to this Hamiltonian evolution algorithm. So there are many others, but this is quite useful, and then I will use this later. So this is very simple example, but this gives you idea on how you do the simulation. Okay. Okay. So having seen some basic aspect of digital quantum simulation, I just want to mention what people are now pursuing, especially looking at the near-term quantum computing. So this near-term quantum computing is roughly based on so-called noisy intermediate scale quantum computer technology. So this technology of quantum hardware characterized by the following. So as I said, the quantum computer consists of a bunch of qubits, and then this available number of qubits are given by, for example, 50 to a few hundred qubits. Okay, and then the quality of each gate operation or qubit itself is not very good. That means that if you do the computation, and presumably there are noises, and then this noise can impose a severe limitation on the computation. So if your runtime is too long, then your signal is overwhelmed by noise. So you cannot extract any meaningful information. In other words, there's a severe limitation in the runtime of the computation. So normally people say, so if you look at this figure, this is one example of circuit, and then width refer to roughly the number of qubits, and depth refers to the, well, roughly speaking, runtime of this simulation. So if your circuit is too deep, then noise is overwhelmed the signal, and then you can't extract any meaningful information. Normally, when you go to the large-scale quantum computation, theoretically speaking, you want to employ so-called quantum error correction in order to eliminate the noise effect or error effect step by step. And then asymptotically, this gives you a very good scaling. So in the future, in the far future, you want to use this quantum error correction, but in the near future, unfortunately, this quantum error correction has a very big overhead. So given the fact that number of available qubits are very limited, you cannot really employ the quantum error correction, and that is why you have to come up with some idea or strategy with a shallow circuit. So that is a very hot topic that people have been pursuing in order to utilize this near-term quantum computers. So due to this, so right now, unfortunately, the quantum computers are not too powerful to simulate in any meaningful way, simulate a quantum field theory. So for example, in this talk, all the numerical analysis presented are based on the classical simulator, mimicking the quantum hardware that will be realized in the future. This is probably I want to just show that how quantum hardware are developing these past years. So this is very brief. So, but this is one benchmarking. So that is, if you can prepare so-called quantum state, so-called GHZ state with a high precision. So this is so-called n-qubit GHZ state. So which is superposition of zero tensor, the tensor product of zero state and tensor product of one state. And in order to prepare this state, you need to have n-qubit state, and also your depth is also roughly speaking n. So following this Hadamard gate, you will apply the series of CNOT gates. So this gives you some idea of how large, how wide, how deep you can go by using the current quantum hardware or the past quantum hardware. So this figure shows how these quantum hardware have been developed. So the x-axis is year starting from 2000, and the y-axis is this size of GHZ state. So, for example, IBM or Google and other companies are developing so-called superconducting qubit quantum hardware, which is represented by this blue box, right? And then starting from 2010, you see that how the size of state grows. And then from this figure, yeah, it looks quite promising, even though I don't know what is happening from now. So this is the current situation, and then we hope that this is growing more and more in the future. So this has been the overview of digital quantum simulation, and then by using those techniques, now I want to get in the talk of quantum simulation of so-called Schwinger model. This is one example of quantum field theory. So before getting into the specific model, I want to briefly point out what is the difficulty that we have faced in a classical approach to quantum field theory. So quantum field theory is composed of a lot of degrees of freedom. So if you try to do large-scale computation classically, then there are too many degrees of freedom and then too much computation. So standard, for example, supercomputer cannot deal with these gigantic degrees of freedom. So instead of phase-free computing this, what people do is people rely on so-called probabilistic approach. More specifically, so-called Markov chain Monte Carlo method is very popular. So I briefly explain that. So let's say you have some operator O. Let's see this Euclidean version. You have operator O, and then let's say you want to compute the expectation value of this operator O. Then in a path integral formalism, what people normally do is you have operator O with the path integral weight exponential minus s phi. So phi is a bunch of fields, and then s is the action of the theory. And by evaluating this quantity, you can compute the operator O. So what people do is that people see this exponential minus s phi as a probability weight of this probabilistic approach. So you basically sample the field from all over the space by using this probability weight, and then based on this sampling, you compute this expectation value. Now, it's obviously important that you have the probabilistic interpretation of this exponential minus s phi. And for example, if you look at this Minkowski version, obviously there's a I factor here. So exponential I, you have to evaluate exponential minus I s phi, or you have to sample based on this, this factor. But this is a phase. So now we're thinking there's no probabilistic interpretation. And even if you try to push this direction, you somehow see a lot of oscillation because this involves a phase factor, and then indeed, if you try to evaluate this function, then there's a high oscillation. So this spoils the probabilistic approach in this Minkowski space. In the same way, even if Euclidean space, for example, if you have topological term in your theory or finite density finite density QCD, then you indeed see that there's some oscillation in this classical action, or sometimes you will have imaginary part in this action, which again induces a high oscillation in this integral. So this doesn't. So because of this, the conventional probabilistic approach doesn't work, and this problem is so-called sign problem. And then due to this problem, people have struggled to solve some part of the problem in the quantum field theory. So obviously, we hope that this can be simulated by quantum computers efficiently. So that is our strong motivation to go into the quantum simulation. So this is very rough strategy of quantum simulation, but so in a quantum computer, what you do is you first prepare the ground state or some other static state, and then as we saw, we applied Hamiltonian inversion, and then at the end, in order to extract these kind of observable, you do the measurement. So that is a basic strategy, but we hope that we can solve some difficult problem that cannot be solved in the classical technique. So now let me get into the Schwinger model and then see how we can apply the quantum techniques that we have, some of which we have already seen. So Schwinger model is just a 1+1 dimension quantum electrodynamics, and then this Lagrangian is given by this form. So you have F, this is the field strength of the U1 gauge field, so this represents the photon, and then you have one component drag fermion coupled to this gauge field. Importantly, we consider the Schwinger model with so-called theta term highlighted by this red text. So because of this topological term, it is normally difficult to solve by using the Monte Carlo technique. Although in this case, because of the 1+1 dimensional feature, you can solve by using other classical technique. But in general, if you go to higher dimension or more complicated theory, then this topological term is very difficult to simulate. So this is a toy model to see what kind of strategy we can take to solve this kind of model. Now, in a context of quantum simulation, it's much easier to use Hamiltonian evolution or Hamiltonian formulation. So instead of using Lagrangian formalism, path integral formalism, we switch to Hamiltonian formalism. So this is a corresponding Hamiltonian. And this pi is a canonical momentum variable conjugate to gauge field A1. So you can think of this pi as electric field of the system. So probably in the normal convention, you can think of this pi as E, electric field E, and then there's a theta term. Now, in a Hamiltonian formalism, you have to explicitly look at the state, the Hilbert space, or the state of the quantum system. And not all the states are gauge invariant because this theory has E1 gauge symmetry. You want to eliminate gauge non-invariant state. In order to do that in Hamiltonian formalism, you have to impose a Gaussian law. So only when this Gaussian law is satisfied, the state that you're looking at is invariant under the gauge symmetry. So at the same, for example, you want to apply the Hamiltonian evolution, but at the same time, you have to monitor if the Gaussian law is satisfied for each state of your interest, because if Gaussian law is not satisfied, then this is not gauge invariant, and you don't want to look at those states. So why are we looking at the Schwinger model? So here's a couple of reasons why we are interested in Schwinger model. So again, Schwinger model itself is very simple. This is just a 1+1 dimensional quantum electrodynamics, but there are many interesting properties that people have been studying, and that is, for example, this model has screening and confinement. And if you look at the ground state, then this model shows the theta vacua, topological vacua, and also there's interesting phenomena, so-called chiral symmetry breaking. And all these properties are very similar to 3+1 dimensional quantum chromodynamics that we are really interested in. So this is indeed a good toy model for benchmarking, and people have used this model to study some aspect or study the quantum strategy to solve some difficult problem. And on top of that, there's good point that is you can, for example, exactly solve this model at massless point. When fermion is massless, you can basically solve this model. So after doing the quantum summation or some numerical summation, you can directly compare your result with exactly solved exact result. Even at the massive point, there are analytical methods available, for example, using mass perturbation that I will mention later a little bit, or even for this Schwinger model, there are a lot of classical numerical techniques available, so you can apply this. And then again, you want to benchmark your performance of quantum simulation. Okay, so this is basically the reason why I want to employ Schwinger model and then try to illustrate what is the techniques that I want to use. So, for the purpose of numerical simulation, I want to employ the lattice Hamiltonian. So you cannot deal with the original continuous quantum field theory, but instead you want to introduce a discretization into each variable so that you can numerically evaluate all these quantities. So more specifically, I will discretize the spatial direction by the spatial lattice. So for example, here, well, the structure of Hamiltonian is not that different from this one, but the difference is that, for example, the integral over the space is represented by sum over the lattice points. And this pi n, the canonical momentum operator or electric field operator is now defined on each link between lattice sites. And for example, this chi is now the fermion defined on each lattice point. So that's the difference. And then there are also some technical difference between this lattice Hamiltonian and original Hamiltonian. But basically, I just based this theory on the spatial lattice. So I will try to simulate this to see some static property of this model by using quantum simulation technique. Now, as we have already seen, if you have, for example, spin Hamiltonian written by X and Y and Z Pauli operators, then you know how to apply the Hamiltonian evolution operator. And then by using that, you can do something interesting. So here again, you want to somehow map this theory in the language of spin Hamiltonian or some operators acting on this qubit state. For fermion fields, there's actually a way to map this fermion fields to spin fields. So that is one way to do that is so-called Jordan-Wigner transformation. So given some fermion field, you can map this to non-local spin operators. So these Z operators so let's say you have a fermion operator on nth site, then you can replace this by the chain of Z operators and terminate it by this x minus iy over 2. Okay, and then same for chi and dagger. And here sigma plus refers to x plus iy over 2, and then sigma minus is x minus iy over 2. But the point is, you can map these fermion fields to spin fields, and then now it seems that more tractable by using the technique that I showed. That is a fermionic part. Actually, it's much trickier to treat this gauge field part. That is because this gauge field, the Hilbert space of gauge field is basically infinite. So the dimension of this gauge field Hilbert space is infinite. So obviously, because your computation resource is limited, you cannot place all this Hilbert space onto the numerical hardware, computational hardware, and especially the size of quantum hardware is limited. You have to introduce some severe truncation into this gauge Hilbert space. So in application of quantum simulation to the gauge theory, this part is quite challenging part, and then many people have been working on this topic. So for example, if you have U1 gauge field, your Hilbert space can be labeled by the electric field eigenvalue of each site. But originally you have infinite level of electric field eigenvalues, but you need to somehow truncate this gauge field in order to place this theory on the limited qubit space. And this part is quite complicated, so I will not getting into detail, but for example, for U1 gauge field, there's several techniques proposed, and then indeed you can map these operators to the sum operators acting on qubits, as detailed, for example, in this paper. And then even more interestingly, now people are looking at non-abelian gauge theory, so that you can apply the same technique to the QCD in the future. So, but anyway, the important point is that given this Hamiltonian, you can somehow map this theory in a form suitable for this quantum simulation. So that is why you can apply the same technique that I showed in the case of the transverse field Ising model. So having obtained the Hamiltonian suitable for Hamiltonian quantum simulations, now I want to talk about how you can possibly see the ground state property or static property of the given theory. So to this end, I here first talk about so-called adiabatic state preparation. Probably you have heard about adiabatic theorem from the quantum mechanics course. But so here, let's say you have H, the Schwinger model Hamiltonian, and then let's say you want to prepare the ground state of this Hamiltonian. then how do you prepare the non-trivial ground state by using quantum device? That's a question that I want to ask. So adiabatic theorem says that let's say you have some initial Hamiltonian H naught, and this is supposed to be very easy in a sense that you can prepare this ground state very easy. So this omega naught is a ground state of H naught, and this omega naught can be prepared efficiently or very easily without getting into a complicated part of the theory. And then you try to non-trivial ground state omega of the target Hamiltonian H. Okay. And then adiabatic theorem says that given this omega naught, you first prepare so-called adiabatic Hamiltonian connecting between this initial Hamiltonian and target Hamiltonian. And then by changing the parameter adiabatically, you try to connect between H naught and H. So this is the adiabatic Hamiltonian HA. Okay. And then using this HA, you implement a time evolution operator. So by applying this time evolution operator with adiabatic Hamiltonian, you want to prepare the approximate ground state omega. Adiabatic theorem says that if you take this adiabatic time t, so basically if you t to be infinity, so you slowly change this adiabatic Hamiltonian from t equals 0 to capital T, then you can indeed prepare omega, provided that the spectrum of this adiabatic Hamiltonian always have a finite gap along this process. So that's the important point. So this is a sketch of the spectrum. So y-axis is the energy spectrum of this adiabatic Hamiltonian HA, and then x-axis is the time. So starting with time t equals to 0, and you will in the end want to prepare the target ground state at t equals to t. Of course, in the adiabatic theorem, it says that capital T should be taken to be infinity. Now, and then you start with some ground state of H naught, and then by changing the Hamiltonian gradually, in the end, you will get the ground state of the target Hamiltonian. But the point is, there's always finite gap between the ground state and the past excited state or some other excited states. So that's a requirement. Now, for the numerical purpose, you cannot take this t to be infinity really. So what you have to do is you have to take sufficiently large t but finite t. And by taking this t to be finite, you will actually get some systematic error. So obviously this error epsilon is inversely proportional to this adiabatic time t. So if you take just a small amount of t, then obviously error is going to be large. And also this depends on how large your spectral gap along the path. So for example, if the gap is very small along the path, then this also increases systematic error. So by this way, you can roughly estimate what is the necessary amount of time for the adiabatic evolution for the numerical purpose. So this is one way to prepare the ground state. In the context of Schwinger model, so for example, for H naught, this is one example of H naught. You can take H naught as a fermion mass term, right? So if you remember, the spin Hamiltonian of the Schwinger model, this M is a fermion mass. So initially you only have this mass term because you can prepare the ground state of this mass term very easily. Okay, and then you prepare the adiabatic Hamiltonian HA, which connects between this initial Hamiltonian and target Hamiltonian, Schwinger model Hamiltonian, with some interpolating function. So this F0 so F0 is 0 and then FT is 1. So initially you will just have H naught, but T equals capital T, T equals capital T, you will end up with target Hamiltonian. So by using this evolution operator, you can actually apply the adiabatic time evolution. And then of course, on the quantum simulation or digital quantum simulation, you apply the corresponding this time evolution operator. And to this end, as we already talked, we use this Suzuki-Trota decomposition And then you can apply the adiabatic time evolution operator by cutting this time into small pieces and then apply step by step this unitary evolution. So although I don't want to get into the details of physics, I just for the demonstration purpose, I will just show you some results that you can get by using this quantum simulator. So again, this is a classical simulator of quantum hardware, but the strategy is adiabatic state preparation that I showed. So here, what I show is the computation of so-called scalar condensate. So this is the important observable that characterizes the static property of Schwinger model. And then x-axis is a coupling constant of the Schwinger model. So this red line represents the exact result. So this alpha panel shows a master Schwinger model. So this exact result for this master Schwinger model. So you can exactly compute this scalar condensate in this model, and this red curve represents that exact result. And then blue data points with error bars are the results obtained from quantum simulation. So this error bar contains both statistical error coming from sampling of the quantum simulation and also adiabatic error that we talk because we have to take adiabatic time to be finite. But you obviously see that quantum simulation gives you consistent result with exact value. So this is an important consistent check that you want to do, and you can do this because you know the exact result for this model. And then now we go to the massive case. So massive case, it's more challenging because you don't have exact result, but still you do have some analytical techniques, so-called mass perturbation. So mass perturbation is, roughly speaking, you have exact result at the massless point, and then by introducing small mass, you can do the perturbation theory and then compute analytically, for example, this scalar condensate as well. So this figure shows again the scalar condensate, but now x-axis is m. M is a fermion mass, and this blue line and green line corresponds to mass perturbation results. And the blue and green respectively correspond to theta equals 0 and theta equals 3 pi over 5. So you don't have to worry about what is this number, but you can think of this as just the theory without theta term and with topological term theta term, okay? And then these data points correspond to the result from quantum simulation. And then, well, from physics viewpoint, it is interesting to see that as you increase m, indeed your simulation results start to deviating from mass perturbation result, because mass perturbation doesn't work if you increase the mass parameter in the theory. And the quantum simulation, well, at least in a small mass region, you see the good agreement between mass perturbation and quantum simulation. But this kind of discussion is something you want to do in the future for more non-trivial problems. I want to go into the last topic. So the one concerning feature of this adiabatic state preparation is, as I said, you have to take this t, adiabatic time t, to be very large, meaning that your runtime of this circuit or depth of circuit is necessarily very long. So if you look at the near-term quantum computing, this is not necessarily very useful, although it might be very useful in the far future quantum computing with quantum error correction. So in order to avoid this very deep circuit, what people have been working on is so-called quantum classical hybrid approach. And then here I give you an idea of how this variational approach, quantum classical hybrid variational approach works. And there are many works in this direction aiming at the realization of the near-term quantum computing. So what you want to do is, so setup is very similar. You have Hamiltonian H, which is written as H naught and H1, and this H naught is again, for example, the fermion mass term in the Schwinger model. And you try to prepare the ground state of this H using a shallow circuit, given the ground state of H naught which is written as omega naught. This is the same setup as adiabatic state preparation. So the strategy is the following. So this is a variational state preparation. What that means is that you have some variational state parameterized for variation parameter. So this is one choice of variational state that is initial. So on the far right, you have omega naught. And then on the omega naught, you apply exponential minus alpha 1 h1. H1 is this part of Hamiltonian. Alpha 1 is one variation parameter. And then after that, you will apply exponential minus I beta 1 h naught. H naught is a trivial Hamiltonian or easy Hamiltonian, I would say. And then again, you have another variation parameter, and then you will apply H1 evolution, H naught evolution, and so on and so forth. So you repeat this process p times. So you have 2 p parameters in total, right? So and these 2 p variation parameters are something you want to choose in order to obtain the ground state of your theory. So of course, initially you don't have any idea what these parameters should be. So maybe you will choose randomly, or using some physics knowledge, you maybe choose some clever choice for this alpha. But what you do is, given this omega, right, you have the circuit representation of this state. So you can compute a Hamiltonian expectation very efficiently on the quantum device, right? So you use this energy function as a cost function for variational approach. So given this state, you have energy function depending on alpha and beta. And then by using this function, you try to minimize, or you try to decrease the energy function by tuning this alpha and beta. So you do a lot of computation to obtain this E alpha beta for many set of alpha and beta. And by using this data, you now feed this information to classical device to optimize these variation parameters. So this is a variation part that is done on the classical device. And then now you have a slightly more optimized set of variation parameters here. So, and then you can repeat this process until this energy function converges to some value, right? And then in the end, if you observe some convergence, you say that, okay, you can use this as an approximate ground state of this theory. So that is a basic strategy of this variational ground state preparation. And then there are many varieties. For example, you can choose a different trial function or different cost function and so on. But this is one strategy that you can take. Well, so here I will just briefly say that, for example, by using this variational strategy, you can prepare the ground state. So this omega is the genuine ground state, target ground state, and this omega alpha beta is the approximate ground state obtained by variational approach, right? So 1 minus fidelity gives 0 if omega and omega alpha beta are the same up to phase factor. So if you successfully prepare the ground state, this 1 minus fidelity should be small. So this is the y-axis, and then x-axis is p. P is the number of variation parameters. So as you increase this p, you would presumably increase the expressibility of the state. So you can increase the possibility that this variational state can capture the correct ground state. And so this is a small scale experiment with some finite theta value. And then as you increase theta, as you increase p, at some point you will see that 1 minus fidelity reaches some very small value. And then this small value, you see a plateau, but this plateau is due to the precision of variational computation. So for this theta over 2 pi 0.3, you will get the ground state with a good precision. On the other hand, there's some difficulty at theta equals 2 pi equals 0.5. Physically, this is because there exists a degenerate ground state. So without imposing some additional condition, it is very hard to prepare the ground state. Finally, I want to mention the comparison between adiabatic and variational hybrid algorithms. So just a brief recap, you have omega naught. This is an easily prepared ground state of H naught. And then you apply the evolution operator practically by truncating this T and also employing the Suzuki-Trota decomposition, for example, for the time reversion algorithm. Now, what is challenging is this very deep nature of this quantum algorithm. So this M is roughly speaking how many times you need to apply this unitary reversion operators, and then for the size of for the lattice size n equals to 100, 10, very small 8 or 10, you already need to apply this unitary reversion 300 to 500 layers. So this is very deep. And also the important feature is that in order to apply this adiabatic theorem, spectral gap is always assumed to be finite. However, once this spectral gap property is known, then this is very useful because you know that if you take sufficiently long time t, then you can reliably prepare the ground state of the theory. So maybe in the when quantum error correction is available in the future, then this is one of the very strong tools to prepare the ground state or access the static property. On the other hand, if you look at the near-term quantum computation, so this C2QA stands for variation quantum algorithm, then you see that this is done with very shallow circuit. By repeating this shallow quantum computing many times, you can obtain a ground state, and then typical depth is just the order 1. This is drastically different from adiabatic state preparation, and then so people expect that this is going to be something very useful in the near-term quantum computing. Now, the challenging part people have addressed and then haven't solved completely is, for example, scalability of this variation approach. For example, we can test like 10 qubit or 20 qubit for now because there's not that powerful quantum computers. But in the future, even in NISQ, you want to simulate like a few hundred of qubits, and then it's highly questionable if you can directly apply the same variation protocol, partly because, for example, if you look at the cost functions, there are many local minima, or sometimes there exists a flat direction in the cost function, which makes it very hard to optimize by using this variation approach. So there are many problems to be solved in order to apply this protocol in the near future. But for now, it seems much more promising if you look at the near future quantum simulation. So finally, I just want to give you a perspective. Well, this is just a summary, but of course, if you want to simulate the quantum field theory, you want to represent this Hamiltonian or system in an efficient way so that your numerical techniques apply. And then what I just mentioned, I briefly mentioned about gauge register, gauge fields, but how you can efficiently represent or truncate these gauge Hilbert spaces are very challenging. And also, when it comes to Hamiltonian evolution, I only mentioned Suzuki-Trota formula, but there are many other protocols available, and then you have to see what is the most efficient problems depending on task. So probably depending on task, you have to carefully choose what is optimal method to do the simulation. In a latter part, I specifically talk about state preparation, and then adiabatic state preparation seems promising as a far-term protocol, but near term, it is not clear how we can directly apply this. So one of the popular methods is, for example, quantum classical hybrid variation method. And then by using this, you can reduce a task of quantum hardware, and you assign some task to classical hardware, and then you can use the shallow circuit, but still you can use this quantum advantage. So that's all I wanted to say, and then thank you for your attention.
Thank you very much. I'll open things up for questions. Does anybody have any questions? Okay, then I guess I can ask some. So you started with the Jordan-Wigner transformation, where you transform from fermion fields to spin variables. Why did you do that? Can't you just stay with the fermion variables?
Yeah, so that's an important question. So as we initially said, so the state of digital quantum computer is especially prepared in a qubit state, and that is 0 or 1 or superposition of 0 and 1. And this already is a state of the eigenstate of Z operator, Pauli Z operator. So it is quite natural and very easy if you have Pauli operators or spin operators. So, and then these techniques, for example, these time evolution techniques are all written in terms of spin operator, and then it's quite obvious that you can directly apply the spin operator on the system by combining with Hadamard gate and other operators. So while I'm not sure if you can directly apply the fermion operator to do this quantum simulation, but it's kind of obvious that if you map this fermion to the spin operators, you directly use the known techniques to do many kind of quantum operation.
But then if you do that, you multiply all these Z operators together, which is fine in one dimension, but then
Yeah.
how do you
So
generalize
that's
that to higher? To two
Yeah.
or more spatial?
Yeah, yeah. So that's a good question. So here, yeah, indeed, I employ the Jordan-Wiener transformation, and we know that this is efficient in the sense that after applying this Jordan-Wiener transformation, the resultant spin operate or spin Hamiltonian is completely local. But as Bob mentioned, if you go to, for example, higher dimension, this non-local operator shows up, and then that gives a bad scaling sometimes. So there are several other alternatives. So I think one of the major ones is so-called Bravik-type transformation. So that is, so if you use Jordan-Wiener transformation, this the size of chain is roughly proportional to system size. On the other hand, this other spin fermion mapping, so-called Bravik-type transformation, only need the log of this system size. So the size of this chain operator is logarithm. So this seems to be an improvement if you go to higher dimension. And then also people have been pursuing other direction, for example, mapping to more by adding some additional ancillary states. Can we make these operators somehow local? So from physics perspective, this kind of direction should be pursued, so that even if we go to higher dimension, we can apply some more efficient simulate the fermion. But in that case, we have to keep track of this fermion statistics. So anyway, these statistics use a non-locality, so we have to figure out how to deal with this non-locality efficiently.
Bob, you are muted.
Hello. Hello, can you hear me?
I can hear you. I can hear you.
Oh, okay, okay.
Oh, I'm sorry, I muted myself. Wait a second.
Oh, okay.
Sorry, I didn't realize I muted myself. Anyway, there's a question.
Okay.
Yep, no. Can you go where you introduced the adiabatic method?
Yeah.
I just wanted to ask, what do you do if you have level crossing? Isn't level crossing a generic phenomenon? That's a rather strong assumption, no?
Yeah, that's a strong assumption. And then generically, of course, you don't know a spectrum between this initial Hamiltonian and the final Hamiltonian. I mean, if you know that, I mean, you have a lot of knowledge about that. So of course, you don't want to assume. So for example, if you know that there's a level crossing, and if you know that what is the connected level, so let's say you have a level crossing between ground state and fast excited state, then you can think of the following. So you first prepare the fast excited state, and then you use the adiabatic state preparation to reach a ground state at the end. So that is one thing if you know that there's a level crossing. Interesting thing is that, for example, if you use the some adiabatic state preparation combined with variational approach. So basically, variational approach helps you to figure out the adiabatic path. Then, even if there's a level crossing, this variational approach automatically gives you some non-trivial paths. For example, you fast excite from ground state to fast excited state, and then after that, you go along this on the same level by using adiabatic process. So this involves optimization. So it's not really original adiabatic state preparation, but as you say, probably yeah. It's a strong assumption, and then we have to come up with some idea, or we have to use at least some knowledge about physics. For example, if you know that between the initial Hamiltonian and the final Hamiltonian, they are all gapped by using physics knowledge, then maybe you can reliably apply this method. But otherwise, yeah. For example, if there's a phase boundary, first order phase boundary, then it's going to be a bit difficult.
Yuta, I think you have a typo in this formula because see, the error is defined by the small gap, but the gap in denominator. So you minimize the gap. So this means the ratio is maximized, right? So you in your formula you should replace minimal by maximal.
Oh yeah.
You understand what
Yeah,
I'm saying?
you're right. So yeah, you're right. You're right. Yeah, thanks. Yeah,
That's a
this
typo.
is Max. Yeah, you're right. Yeah, thanks.
Of course.
Thanks. Yeah. Yeah.
Very good. Are there any questions? Vladimir, do you have any questions besides correcting his min-max?
You know what? I think it's a really nice lecture, and that was a typo, just cosmetic improvement. Otherwise, it's just really good lecture. I think maybe it will be useful. Well, we can have private discussion later. I have some private ideas, but we'll meet with Kikuchi later. Thanks.
Okay, then if I can ask for the benefit of the students, so do you think this is a field that's worth going into now? Do you think there'll be progress where we'll have large number of qubits in the next 5 years, 10 years?
Yeah,
Why
so-
should a
okay,
student go
this is-
into this field? Or are they just going to waste their time for decades? Is
Yeah,
this still
so,
being recorded?
Yeah, so I mean, as I said, this near-term quantum computing is going to, well, people expect this to be realized in 5 to 10 years, for example. And maybe I will show some slides that I didn't use. So this is this is quantum hardware roadmap that Google and IBM announced a while ago. So they say that, so now, well, in principle, you have an access to the 60 qubit machine or this kind of order machine. And of course, the problem is if noise is well controlled, or you can mitigate error or so and so on. But this near-term quantum computing is coming very soon, possibly in 5 years or so. So if you are interested in the application of quantum computation in the near future, then of course you should start something. And then there are already a lot of problems. Again, although people are interested in variational quantum algorithms, there are many problems, and then you cannot very directly apply in order to do the larger scale computation, like 100 qubit simulation, because of some problems pointed out in the variational quantum computation. Now, then the question is, let's say we want to do the quantum field theory simulation, and then it seems that the number of qubits and then depths are intractable even for the near-term quantum computing. But still, there are a lot of things to develop. For example, as I said, the Hamiltonian formation of quantum field theory is not the mainstream compared with what we have seen. Normally, people have worked on the path integral formalism. So, and then you have to think about the truncation of gauge field and quantum algorithm and so on. So there are many things to solve. And on top of that, let's say in 20 or 30 years, we want to apply the quantum error corrections. I think we already have to start because, for example, in a company like IBM and Google, they already started developing this quantum hardware suitable for some specific quantum error correction scheme. They started or they will start. So if you have an idea and then if you have suitable quantum error correction technique, then you have to start thinking about developing this quantum hardware for now, well, now or in a couple of years so that they can develop this quantum hardware, which is possibly useful in 20 to 30 years. So, well, there are many things you can do now. And maybe for especially theorists, for example, it's very, very fascinating to join this field at this point, knowing that in 20 to 30 years, something interesting is going to happen. So I think it's a good time to join this field now.
Very good. I just had to ask. Okay, well, if there are
Yeah, I
no other,
know.
if there are no other questions, then let's thank Yuta again for a very nice talk. And
Thank you.
with that, I'll close the session.